So, welcome everyone. Thanks for coming in a very busy November towards the end of the year. And I know calendars are full, so I greatly appreciate the attendance. And we have many more people online. I also greet those who are following us in the stream. And first of all, of course, I want to welcome our guest of honor, Professor Elisabeth von Hauff. Welcome. And we are very honored to have you here. And I welcome the members of the respective faculties, our students, and members of the scientific staff, of course. And today we also have a colleague from our University of Applied Sciences, Professor Imke Salchert. Thanks for being here. It's great. So I'm particularly pleased today because today, again, we are giving the floor to a female scientist, and we are welcoming another female scientist of top and outstanding ranking and international visibility to our TUD community. And she has been, on top of that, has been appointed in a discipline that is electrical and computer engineering that at all levels of the academic hierarchy is still working very hard, and I'm looking to the dean, to increase the proportion of female scientists and at all levels of our scientific and academic hierarchy. So this makes us very happy and very proud. Elisabeth von Hauff also represents and highlights the interdisciplinarity of engineering sciences at TU Dresden in a prototypical manner, I'd like to say. Elisabeth finds her scientific home in a field where physics, chemistry, and electrical engineering join forces, organic electronics. And yet, in another respect, Elisabeth von Hauff's appointment is strengthening our strengths, and that is the close cooperation with our research partner institutions under the umbrella of the Dresden Concept Science and Innovation Campus. So in three very particular ways, Elisabeth is just more than a perfect match. It's wonderful. And Elisabeth von Hauff has been appointed last year to be Professor of Coating Technologies for Electronics at our faculty. And at the same time, she has been nominated and received the appointment as director of the Fraunhofer Institute for Organic Electronics, Electron Beam and Plasma Technologies, for short FEP. And those of you who are familiar with our very diversified Fraunhofer landscapes have probably learned by heart all the acronyms of all the different Fraunhofer institutes. I'm still on my way, but FEP sticks with me for sure. And you may know or may not know, I tell you now that under the umbrella of the Dresden Concept Science and Innovation Campus, we are bringing together more than 30 research and cultural institutions that have joined forces here in Dresden. More than we've estimated 12,000 researchers and scientists are working in and around Dresden on this campus. And one of the 9 Fraunhofer institutes that are part of the Dresden Concept Alliance is the FEP, as I just mentioned. So now let me also tell you that the fact that TU Dresden is in this year, actually in November 2022 is the exact time we are celebrating our 10-year anniversary of being an excellence university. And this has a lot to do with Dresden Concept and this alliance that has been forged around that time, 10 years ago, and maybe 10 to 12 years. And in that tradition, it's not very surprising that FEP, under Elisabeth von Hauff's leadership, is contributing to one of our clusters of excellence, the CT cluster, tactile internet with human in the loop, but also to a number of collaborative research centers funded by the DFG as well as research training groups. And we're very grateful for this very productive and fruitful collaboration with our colleagues at Fraunhofer and in particular with FEP. The strategically positioned joint appointments with non-university research institutions is one of the most important tools that Dresden Concept has to substantiate this alliance and to create synergy, to push the scientific boundaries and to create innovation. All of our research institution partners from outside bring in their own perspectives, their own logics, and it's then combined under the umbrella of Dresden Concept with the logic and the strengths of a state university. Of course, it goes without saying that organic electronics and Elizabeth's research on energy technologies are at the right time, at the right place, I would say. So she's really asking the questions, we will hear more about it in a little bit, how we can tender materials to create functional interfaces for energy conversion and sensing with a small CO2 footprint, I like to add. And I would also like to mention, because it is an important part for us as TU Dresden as a modern place for research but also for working, that we are not only bringing Elisabeth von Hauff to our campus and to the TUD community, but also Professor Florian Mintert has joined our community here. We were able to find a very good match with his expertise. He has been affiliated with the Helmholtz Center in Rossendorf, and besides his continuing professorship in physics at Imperial College in London, he is coming regularly to work with groups in Rossendorf, and I'm welcoming the colleague from Rossendorf who is here with us tonight. So we are extremely pleased to have you both in Dresden, and therefore I'm expressing a very warm welcome to you and to Florian to be becoming and being members of the TU Dresden community, and let's just applaud at that stage. Now, for those of you who have been loyal watchers or attendees of our inaugural lectures, you are aware that after me there will be two more people giving an intro to Elisabeth and why she's here. The first one will be taken on by our Dean of the Faculty of Electrical and Computer Engineering, Professor Karl-Heinz Bock. Thank you very much for that. And the second one will be given via video by Christoph Lyons, Professor Christoph Lyons, who is a member of our Faculty of Mechanical Engineering, and he at the same time is director of the Fraunhofer Institute for Material and Beam Technology, IWS, the other acronym you shouldn't forget. And they will introduce the strategic role of this chair within the university and for our collaboration, as well as, of course, present us with a good laudatio for Elisabeth as a scientist and a scholar. And at this point, I'd like to thank all the people who made this event possible. It's our chief of protocol. It is many colleagues at the Faculty of Electrical and Computer Engineering, and personified by the Dezernent, Tanzmann. Thank you very much, as well as colleagues at the FEP, I'm sure, and colleagues at our communication office who make sure that the stream is working well and that it is put online afterwards. And as you know, after the lecture there will be a Q&A, but then also there will be plenty of opportunity afterwards at a reception over a glass of champagne or whatever else you would like to drink and some tidbits to eat, to get into a conversation with our new member of the TU Dresden community. And with saying that, I'm turning over the microphone to our Dean, Professor Bock. Please join me on stage.
Thank you very much, Magnificency. And it's my great pleasure to be here to introduce our inaugural lecture. And so first of all, Magnificencies, Spectabilities, dear colleagues, dear students, dear guests. I'm very pleased to welcome you, Professor Dr. Elisabeth von Hauff, at our Faculty for Electrical and Computer Engineering of TU Dresden, and to contribute to your personal introduction today at your inaugural lecture. So, Professor Elisabeth von Hauff, I would like to introduce her, her CV a little bit to you before we go to what we have announced to bring you into the background of our faculty. So, Professor Elisabeth von Hauff studied physics at the University of Alberta in Canada and received her Bachelor of Science in Physics with honors in 2000. After moving to Oldenburg, she received her Master of Science in Renewable Energy Physics from the University of Oldenburg just 1 year later, in 2001. She started her scientific career in the role of research assistant at the University of Jena and as a PhD research assistant at the Institute of Physics of the University of Oldenburg, where she received her PhD in 2005. She continued as research group leader for organic electronics at the University of Oldenburg and received her habilitation in 2011. From 2011 to 2013, she worked in a joint appointment as associate professor in physics at the University of Freiburg and at the Fraunhofer Institute for Solar Energy Systems, ISE, in Freiburg too. Yeah. And from 2013 and until 2021, she was appointed as an associate professor in physics at the University of Amsterdam, where she received a special appointment in 2021 as a professor in chemistry. So as you can see, it was really a very nice career and very smooth and targeted and aimed development of herself, so very impressive. Since 1st of June last year, 2021, she is jointly appointed as a professor of coating technologies for electronics in the Faculty of Electrical and Computer Engineering and as a director of the Fraunhofer Institute for Organic Electronics, Electron Beam and Plasma Technologies, FEP. She received several awards, amongst the Mercator Fellow in 2016 and the Open Mind Award from the Dutch Research Council in 2019. Professor von Hauff's core research aims for the challenging topic of interfaces between functional materials, since these are the places which define the functionality and performance of devices for energy conversion and storage technologies, such as solar cells and batteries. So it's actually the core topic to make them work, yeah? And this is the target of your research. So with this, she represents the research field of semiconductors, organic and 2D, thin films, interfaces, and photovoltaics, which is integrated within our faculty in a very synergistic way. The research and development profile of the FEP, and in particular, the research topics of Professor von Hauff are linked to 3 of 5 of our research profiles of the TU Dresden. And they overlap very well with the 4 research profile lines where our faculty is connected into the strategic background of the TU Dresden. So it's really a nice fit, and we are very happy about that. So her research work contributed, for example, to the health sciences, biomedicine, and bioengineering, which is one of our research profile lines. And she made significant contributions to functional materials and material sciences, also a research profile line. She contributed to the field of energy and mobility and environmental compatibility and sustainability, which is also a research profile line. So it's a very nice fit, and we can be very happy to have you here. So with her research work, particularly in the field of organic electronics and 2D, including special functional materials, transistors, and solar cells, she is also directly involved in the advance of information technologies and microelectronics at our faculty. And in particular, this research profile contains areas of the very highest strategic importance for Dresden, but also for the, of course, Saxony and for above, yeah, or beyond. So it's the largest electronics location for microelectronics in Europe. Approximately 50,000 people work in about 1,500 companies in this environment of microelectronics cluster, Dresden. So due to a very targeted appointment policy, the scientific competence of the TU Dresden today covers the entire spectrum, from basic and applied research in the field of data storage, processing, transmission, to the development and testing of new materials, for example, for nanotechnology and bionics. So Professor von Hauff excellently fits to this interdisciplinary research environment with contributions bridging from the basic research to the advanced technology development, since she has the two positions in our faculty and at Fraunhofer. There are close connections to several regional Fraunhofer institutes and numerous joint ventures with global companies, such as the acquisition of the BMBF top cluster Cool Silicon, the Research Cluster Center for Advancing Electronics Dresden, CFID, the Cluster of Excellence Center for Tactile Internet with Human-in-the-Loop CETI, the new 6G Live joint initiative between TU Munich and TU Dresden, and as well the new SEMECO Cluster for Future, representing the cutting-edge research environment she has joined. Professor von Hauff is already actively involved in the current planning for the new large-scale research initiatives, including the New Excellence Initiative. Since the beginning of her work, she has also been a member of the Faculty Council in Academic Self-Administration. Just from the beginning, she joined us already. Usually, people take some time to do that. Huh? She has been there and provided already her support. And since then, she also works on various doctoral committees and in supervising already her doctorate studies. She is now currently setting up her own research working group at her chair at the faculty here at the university in parallel and in synergy with her research environment at FEP. So also here she directly started actually to support our faculty. So for her very dedicated direct involvement within and for our faculty, I would like to express my heartfelt thanks on behalf of our entire faculty. And I express our deepest appreciation. So we are therefore very pleased that with our colleague, Professor von Hauff, we were able to welcome an excellent member to our faculty and that we are once again respectfully emphasizing this at the occasion of your inaugural lecture today. So thank you very much and cordially welcome.
Dear colleagues, dear students, dear guests, it's certainly my great pleasure and honor to welcome you all to the inaugural lecture of Professor Elisabeth von Hauff. Her background is in physics, and after a very competitive selection process, she was appointed to the chair of coating technologies for electronics at the Institute for Solid-State Electronics at TU Dresden last year. She's now also the new director of the Fraunhofer FEP, the Institute for Organic Electronics, Electron Beam and Plasma Technology in Dresden. Together with Fraunhofer IKTS, Fraunhofer IFAM, and Fraunhofer IWS, led by Professors Michaelis, Weisgerber, and myself, we are located at Winterbergstraße in Dresden, forming a major materials-oriented and centered Fraunhofer innovation hub. The collaboration between TU Dresden and Fraunhofer is building upon a very successful partnership within the Dresden Concept Research Alliance. For example, currently more than 60 PhD students and over a few hundred undergraduates are working in jointly organized and used labs at our Fraunhofer campus at Winterbergstraße. And I'm pretty sure that Elisabeth von Hauff will further strengthen and provide her impact to this collaboration. This partnership is for the benefit of the university and the Fraunhofer Institutes at the same time. Together we are training tomorrow's academics and technical workforce in high technology fields and develop solutions to address societal challenges. In a strong partnership, we are bridging the gap between fundamental research and industrial application. A clear benefit for society and industry, one of the pillars of our country's prosperity. Elisabeth, it's very good to have you as a new member of the TU Dresden, and I'm more than happy to have you as a strong collaborator on our Fraunhofer campus. All the best to you and your team, and best successes.
Really, I'm very honored, Professor Staudinger, Professor Buck, Professor Lyons, for your very kind words. For me, it's really a great honor to be here, also to be in Dresden. It's an incredible environment, not even for the size of the city, but just the amount of research and interdisciplinary research that's going on here, it's incredible. So thank you very much for your warm welcome, and I'm really looking forward to our cooperation. Thank you too for the opportunity to present here. I understood it's a lecture series, and I'm very, very happy to be part of it. Yeah, so what I want to talk a bit about today is energy technologies, and I have the slightly cryptic title that the magic is at the interface. So, just a small, important fact before I start. In 1 hour, so in roughly the time I'm going to talk to you and you're going to ask me questions, the amount of solar energy that hits the Earth is actually enough to supply what humans consume over 1 year. Yeah, so what's the problem, right? So that's sort of the focus of my talk. So in my group, we actually focus on interface sciences and in situ tools for diagnosing new types of electronics. Solar cells, diodes, transistors, sensors. But what I want to focus on today is the work that we've done in solar energy until now. So why is it that all of this solar energy hitting the Earth is not being put to the use that we could be putting it to? So that's the question. The magic is at the interface. So when I talk about interfaces, I'm actually talking about different interfaces. As a scientist or an engineer, of course, I'm talking about material or device interfaces. But I can also be talking about interfaces between policy and technology. So how do policies impact how solar energy, for example, is being implemented? This is also work that we're sometimes looking at. Or if I have a very, very interesting lab result, why am I having trouble turning it into a viable technology? So this is actually a question that we're looking at in the Fraunhofer Institute. And what about really the innovations in energy technologies, new materials, new device stacks, new interfaces? This is the sort of thing that we would look at then at the university. So just to start with photovoltaics, if you look at this chart, this is actually a very, very nice service provided by the National Research Laboratory in the United States. And what it shows are all of the record efficiencies of photovoltaic technologies starting in the 70s and coming till now. And what's interesting about this chart is that we don't see that one single technology is sort of pushing out or dominating over other types of photovoltaic technologies, but rather we see that there's an entire zoo of new technologies that are being developed. So that now in 2022, we have so many different technologies that I can't even list them, and I won't do it either. So what's the difference between these technologies and what determines whether a technology is feasible or not? What you see is sort of a range of some commercial technologies, but also some emerging technologies that are still being developed in the laboratory. And the point is that if we look at photovoltaic technologies, there's sort of an unwritten rule. It's called the golden triangle. And this is sort of what determines whether a photovoltaic technology is commercially and technically feasible. So what this means is we look, of course, at efficiency. So how efficiently does a solar cell convert light into electricity? But what's also important are things like cost. Of course, it has to be possible to produce solar cells and to implement them at costs that are competitive with conventional technologies, but lifetime. So how reliable is the technology? And that's where, in research, we're usually trying to fix sort of the challenges of new materials and new devices. Why is it not as reliable as we think it should be? There's a host of other political and technical questions like the acceptance by the public, toxicity of materials, throughput, processing of materials. And generally, if we use this golden triangle to sort of assess how feasible a technology is, we try to assess also its grid parity. So grid parity is basically a measurement of whether an emerging technology produces electricity or produces power at the same cost as conventional sources. And we do this by looking at something called the levelized cost of electricity. So what this is the total system costs of an energy technology divided by the total energy production over its lifetime. Sounds very simple. I'll show you that it's not exactly that. So if we look at commercial technologies, for example, silicon photovoltaics, we'll already see that this is a little bit of a complicated question. So silicon photovoltaics is essentially well over 90% of the photovoltaic market. It's a commercial technology. There's still a lot of research and development being done on silicon photovoltaics. The questions focus around making thinner wafers to save material, to lower costs, and to come up with strategies for absorbing more light into the solar cell, so improving efficiency and lowering cost. And so with a PhD student in Amsterdam, Wang Rong, we did a very interdisciplinary project. So I worked together with her co-supervisor, Bart Bossink, and Sandra joined our group a little bit later. And we thought, okay, let's look at photovoltaics from a technical perspective and from an economic perspective, and try to ask the question whether silicon photovoltaics has really reached grid parity or not. There's a lot of conflicting reports out there. So what Wang Rong did is she decided that China could be an interesting case study. And the reason China is a very interesting case study to look at grid parity for silicon photovoltaics is that on one hand, they have an enormous amount of installations, way, way more than anywhere else on Earth, certainly 10, 100 times more than what we're seeing in Europe. It's the largest market, the largest producer. It means the costs of photovoltaics are also the lowest in China. Now, the more installations you have, the lower the cost. But what we're seeing in China now is that the subsidies are being decreased. So what we're seeing on one hand is a decrease in photovoltaic cost due to increasing installations, but a decrease in subsidies, meaning an increase in cost. And the question is, what does this mean for grid parity in China? And how can we translate this into other markets? So what we did is we looked at photovoltaics specifically as a technology. It's not the same as a coal-fired power plant. And we looked at what happens if you include the costs associated with the system of photovoltaics. So that means including costs associated with integrating photovoltaics into the grid. And we call this the system LCOE. Now, what this means is we look at the generation costs and the system costs over the entire lifetime of the photovoltaic module. And with silicon, this is actually not as difficult as with other technologies because we know the lifetime of silicon modules. That means that if we know the costs going in, we can get a relatively good estimate of the electricity costs from silicon photovoltaics. So what we did is we looked at the total cost balance, and this is shown to you in the top left-hand corner, and we see that actually if you consider the system costs, this makes up about 15% of the total costs of the photovoltaic market, of the total photovoltaic cost of these modules or of these installations. And so if you factor this into the electricity prices, you can work out the system LCOE over time. So this is on the lower left corner. What we see is a gradual decrease, and this is simply a learning curve that the more installations we have, the lower the cost goes over time. And so what we did is we defined a very simple parameter, the grid parity index, and this just is simply the system LCOE, so the costs, over the conventional electricity price. And so if we can produce electricity from these modules or from these installations at a grid parity index of 1 or lower, then we've reached grid parity. This means that we can produce electricity for the same price or lower from these modules. And so we looked at all the provinces in China. And the issue in China, of course, is that also the electricity is very, very cheap from coal-fired power plants. So you're actually competing with a very, very low cost of electricity. It makes it also a little bit less trivial. And what we found is simply by considering these system costs, we simply can't get anywhere close to the conventional electricity price with these photovoltaic modules. So this drop in subsidies is causing an increase in the price that is simply making photovoltaics a more expensive technology. So based on the prediction of the decrease in photovoltaic prices over time in China, what we see is that we won't actually reach grid parity in China till this year or 2030, depending on the province. Depends a bit on the local electricity price in each of the Chinese provinces, also on the solar irradiation that you have locally. Okay, so this is a very techno-economic example of some of the challenges we have in photovoltaics for a technology that's actually fairly well understood. What happens if we start to go to emerging technologies? So this means that now we have questions that arise between results that we get in the laboratory and turning these or translating these into real applications. So now silicon photovoltaics has been commercialized, but what does this mean for solar cells that have not yet been commercialized, where we maybe don't have as accurate assessments for performance parameters, meaning we don't know the lifetimes, we don't know the efficiencies. So I'll look at organic photovoltaics. This is the field I've been working in most of my scientific career. And organic photovoltaics is a very interesting branch of photovoltaics. So what you can see here are all the orange dots, they represent emerging photovoltaic technologies. So there's a range of these. It's an entire family of new technologies based on thin film technologies that can be produced at low temperatures, low cost. What this means is we can go away from rigid types of solar cells towards flexible, light types of solar cells that can be integrated into completely new applications. So in the case of organic photovoltaics, we're talking about solar cells that are made from molecules. Often they're solution processed, sometimes vacuum processed, but processed at temperatures that are low enough that you can actually implement them onto plastics. And in principle, this is very promising because it means we could produce low-cost photovoltaics in a large volume. And just a very brief history of where this technology started and where it is now. When I started my PhD, our benchmark was a 5% solar cell. And so what we had was a polymer and a fullerene. So the polymer was what we call the electron donor, and we have the fullerene, that's the electron acceptor. If a photon comes in and excites the polymer, it donates an electron to the fullerene, the acceptor, the electron acceptor. And there were hundreds of PhD students, maybe thousands, working all around the world trying to get a 5% solar cell. And finally, somebody did it. They controlled the structure of this polymer fullerene layer, and we thought, we're almost there. And we thought, if we can get to 10% with this technology, it will easily be commercialized. Because it's just so attractive, everybody's going to want to have it. So the chemists really started to work hard. It's a very interdisciplinary field. You have physicists, engineers, chemists working together. The chemists got very excited and they started to make new molecules. And so what you can see here, and this was a breakthrough above 5%, is something called a donor acceptor molecule. So what we have is on our donor molecule, we have a character of an electron-rich and electron-poor region on the molecule, and this contributes to a broader light absorption. So you can actually absorb more solar photons, and it prevents carrier recombination. It prevents electrical losses. So we suddenly had new molecules that could absorb more light and yield better electrical performance. And we're almost at the 10% mark. Then recently, the non-fullerene acceptors came. This is about 5-6 years ago. And so now we have donor molecules with a donor acceptor character, and now we have acceptor molecules with a donor acceptor character. So basically what this means is we have two molecules that have very, very broad absorption, very, very interesting electrical properties, and we're almost at 20%. And we're still not commercialized. A few years later, where are we? We're well over 20%. If we look at tandem cells, very, very competitive efficiencies. Now we've moved away from two molecules and we have an entire class of molecules. So organic photovoltaics is no longer one technology, but it's an entire class of technologies. Small molecules, large molecules, good absorption, reaching 20% if we get them into tandems, almost 20% in single junctions. So I had two students in Amsterdam. They were at the University of Amsterdam, and they were master students, Isabella and Floris, and they said to me, Elizabeth, we're so interested in organic photovoltaics. We want to start a company and we want to produce them. And I said, okay. Actually, it's good because younger people who come new into new fields, they have totally different ideas and they're not burdened by the history, right? I'm burdened a bit by the history because I knew, okay, 5%, 10%, 20%, it's still not happening, right? They came in, they were so excited. Actually, what they wanted to do, because, well, in the Netherlands, this is a good idea, is to put organic photovoltaic modules all over greenhouses. I said, okay, guys, I will do this on one condition. COVID came along, so this was actually a good thing to do. We sit down together and we write a very critical perspective on what are the parameters that we would actually need to achieve in order to make this technology commercial, feasible. I said, okay, so maybe we can define threshold values for not just efficiency, because we have very high efficiencies in this technology, but what about lifetimes? Because often with thin film technologies, the problem is the reliability. You don't know how long this technology will last. You have 18% maybe for a few days, but how long How long can you actually rely on this technology to give you the performance that it gave you when you first made the solar cell? And the cost. And essentially, these parameters are all entwined. Of course, if I have a more efficient technology, it's somehow cheaper. If it has a shorter lifetime, it gets more expensive. So can we do that? Can we actually, based on the literature, come up with threshold values? So very important point about photovoltaics is something called the scaling gap. So I showed you a bunch of record efficiencies, but these are the efficiencies that researchers make in the lab on solar cells that are 1 centimeter by 1 centimeter. What happens if I want to take this solar cell that's 1 centimeter by 1 centimeter and turn it into 1 meter? And that's the beauty of thin film photovoltaics. I don't just have a wafer like I do with silicon, where I just hook up a lot of wafers together, but I create large-scale modules. So this idea of upscaling is a very important part of the technology. And generally what we see, of course, it's quite intuitive, is that the efficiency drops as soon as we start to upscale from 1 square centimeter to 1 square meter. Of course, cells in the lab, I mean, you can produce them with very expensive, slow steps, high purity. Once you go to fabrication, you have to actually take some compromises in the purity and in the production just to lower the cost. So what do we see? Well, we see that the efficiencies of modules are considerably lower than that of cells, and this is known as a scaling gap. And this is usually a very large number for immature technologies or emerging technologies. So what you can see here are 3 examples of modules over time from 2009 until around 2021, where you see that the scaling gap for organic photovoltaics is between 30 and 40%. Now, that's not enormous. For silicon, it's also 20%. The problem is that it's just not very reliable for organic photovoltaics. And of course, the scaling gap increases if you have breakthroughs in the lab. So if you actually get higher efficiencies through new breakthroughs in materials, then you have a larger scaling gap. And then as production slowly catches up, the scaling gap closes down. Now, what does this mean for trying to define a threshold value for efficiency? Well, these are, what you can see here in the gray dots, these are predictions from the literature of how efficient a solar cell technology would have to be commercialized. And you can see there's no trend, it's scattered everywhere. The problem is that nobody really knows because we don't really know which application field these solar cells are going to be applied in. Everybody's fairly sure they're not going to come on your rooftop, but are they going to be on my clothing, indoors? Are they going to be outdoors? Are they going to be on windmills? Are they going to be on greenhouses in the Netherlands? We don't really know, and if we don't really know that, it's very, very difficult to specify what sort of efficiency we require for the costs of that particular application. So we don't actually know how to define the LCOE for these emerging technologies simply because we don't know the total system costs if we don't understand the efficiency. Efficiency is always measured on very standardized conditions. But of course, if I'm using my technology under non-standard conditions, I don't have the same efficiency anymore. And also, if I don't know how long this particular technology will last for the particular application specifications, I also don't know the lifetime. So what about the lifetime? Actually, this is sort of the crux for almost all thin film photovoltaics, and especially for emerging photovoltaics like organics. Lifetimes of commercialized solar modules are always given to be around 25 years. Often they're longer. So what we see with silicon is it actually has a much, much longer lifetime than 25 years, but you have a guarantee for 25 years under very standard conditions. And we simply cannot guarantee these type of lifetimes for emerging photovoltaics. The question is, does that matter? Well, what does matter is that we can't define any lifetimes. So again, what you see in the gray points these are defined lifetimes for different modules in the literature. And you can see, again, there's no trend simply because the testing conditions are all a little bit variable. And this is because for commercial modules, we have very standardized testing, and for emerging modules, we simply don't. So this is just an example of protocols for determining lifetimes in thin film photovoltaics. These are international standards that have been defined for all the 3 categories of photovoltaics that are found on the market: crystalline silicon, thin film, and concentrator. And so basically what you have is you have a bunch of modules and you put them through different stress tests. You have a control module, you have one that's put through outdoor tests where you cycle the temperature, you cycle the irradiation that it receives, and you basically subject it to thermal stress, humidity stress, lighting stress, and you look at how the efficiency evolves. Now, it's not that you wait 25 years to see what happens with this module, but you do very extensive stress tests that go well beyond what you would expect outside. And because these are well defined, you simply look at where the efficiency of the module drops to 80%, and that's the lifetime. So what the community did, the organic photovoltaic community did, is said we need standards like this, but they have to be specific to the technology that we're developing. So the ISOS community, International Summit for Organic Photovoltaic Stability, got together and defined a bunch of protocols that vary in complexity. So very, very simple protocols of just storing the devices on shelves in the dark and monitoring the performance over time, to exposing them to different lighting conditions, to exposing them to thermal stress. And what they did is they defined the lifetime as being the time at which the performance of the solar cell or the efficiency of the solar cell drops to 80% of its initial value. And it's very important because most emerging technologies show something we call a burn-in. So you can see a rapid drop in that power conversion efficiency in the beginning of the lifetime of the solar cell, and then you get a gradual drop. So what you want to do is you want to define the performance loss until the burn-in stops, and then afterwards, and look for the lifetime. So that was quite an interesting concerted effort where internationally people really got together and said we need standards even just for research cells so that we can compare the results that we're getting from different laboratories. And the benefit of this is, of course, you have protocols that are suitable for any type of laboratory, from the very simple to the very, very sophisticated infrastructure. Okay, so we now have a few parameters to try to define where we want to go for a technology. Now we can go into the nitty-gritty. Where are the failure mechanisms? We know how to define them. Maybe we know how to define lifetime now for an emerging technology, but why is my solar cell failing? Well, if we look at basically the anatomy of any thin film solar cell, they all kind of look the same. So in contrast to silicon, where you just have a silicon wafer and some contacts, here we have multiple stacks, multiple interfaces of materials. And so what you see is you have the active layer in the middle. This is the semiconductor. This is where I absorb the light. This is where the photovoltaic energy conversion occurs. But I also have transport layers and I have contacts. And so I combined a series of materials with very different physiochemical properties. I turn the light on, I let a current run, and really a lot of things can happen. So in the active layer, this is where photovoltaic energy conversion occurs. A photon comes in, it excites an electron from a lower energy level to a higher energy level. And what's common to all solar cells is that I have an energy gap, and that this energy gap essentially is responsible, together with the light, for giving me a voltage in this solar cell. So if I understand actually the electronic properties of a material, I know already the voltage that I can get out of this solar cell. So the optical band gap of the material essentially determines the voltage that I get in this solar cell. It's determined by the chemical potential of the carriers in the material. Okay, but then what I need is either a homojunction or a heterojunction in my active layer. So what does this mean? Either I create a difference in the doping density in my active layer so that I can create a band bending, or I interface two materials with different electronic properties to get a heterojunction, because I need a rectification for that current. I need to create a directionality for the flow of current in my solar cell, and this is where the photocurrent comes in. Then I have my transport layers. The transport layers are there to align perfectly to the active layer to extract the photocharge to the external current. Now, this is probably the largest challenge. Sounds very trivial, but it's the largest challenge that we seem to be facing with most emerging photovoltaics, is that you need materials that are highly conductive, yet chemically inert, and perfectly energetically aligned with my active layer. Essentially, that doesn't exist. So essentially, we're always looking at some form of compromise or some form of interfacial engineering in order to achieve this particular situation. So what can go wrong? Well, obviously many things. So what we typically see in solar cells is that you have the formation of what we call energy defect states. And these form in the band gap. So it means that I actually lose photocarriers that I've generated over these defect states. They tend to recombine. Drop in photocarrier. What I see is a drop in voltage when I have these trap-assisted recombination processes. Maybe I have chemical reactions occurring over time, or ion migration. So ions are also charged particles. If I have an electric field across my solar cell, I'll also see ion migration. And if I look at the solar cell characteristics, it's very, very generic. So any solar cell will show me these characteristics. What I have here are the current voltage characteristics. So if I simply illuminate my solar cell, apply a voltage, measure the current, I get this very, very characteristic curve. And I can assess the solar cell efficiency based on this curve, based on the open circuit voltage, which is the largest voltage in the cell when no current flows, the short circuit current, largest current through the cell, and the fill factor. And essentially what the fill factor tells me is the largest sort of square that I can fit into these JV curves. It essentially defines the maximum power point of the solar cell. So what is the efficiency? Well, it's the maximum power coming out of the solar cell divided by the input power. So these particular solar cell parameters determined by the optical band gap, they're determined by the quality of my heterojunction, determined by the density of defect states, will determine all of these three relevant global parameters for solar cell efficiency. But how do I actually understand microscopically what's going on in the solar cell? And this is where we go into the nitty-gritty. So I want to understand time-dependent processes in a semiconductor, in a solar cell. I see some people sitting up straighter. I see now we've gotten to the science. Yeah. So what I look at is the permittivity spectrum. So what is permittivity? Permittivity is a measure of how any material interacts with an electric field. And so if I have a solar cell, I have a material or a material system interacting with a changing electric field. And I'm going to have a number of processes. Some of them are ideal photovoltaic processes. This means the transport of charge. And in the case that I have a non-ideal solar cell where I have a decrease in performance over time, I'm also going to have chemical reactions, dipolar orientation, wandering maybe of ions, and particular things that react to the electric field that are not contributing to the photovoltaic energy conversion. So this is actually what I want to understand. I want to try to quantify the characteristic timescales of these non-ideal processes in order to understand why my solar cell performance is not ideal. So if I apply an electric field to a material, what I see generally is either it will be dissipated in the form of current flow, so I'll have heat generation, current flow, or it will be stored. And generally what we see in solar cells is I have a mix of these sorts, either dissipation and storage, depending on what the process is and depending on the frequency or depending on the time scale that I change the electric field. And so what I can do is I can measure either the complex resistance or the complex conductivity, the admittance or the impedance, and I can try to extract the timescales of these processes in order to understand what's happening microscopically in my solar cell. So what do we do? Well, in my group, we apply a lot of impedance spectroscopy. It's a relatively easy measurement to perform, but it's a relatively difficult set of data to interpret. So essentially what we do is I go back to my current voltage characteristic and I pick an operating point, like the open circuit voltage. And then I just electrically perturb my sample. So I apply a small signal AC voltage to my sample, and I measure the small signal AC current response. And what I typically will see is a slight time delay between the voltage input and the current output because I have some mix of dissipative and storage processes in the sample. So what I do is I look at the impedance, which is simply a transfer function given to me by the input voltage, the output current, and I look at this as a function of frequency of the input voltage. So what I get is a frequency spectrum of the complex resistance. So I get data that looks something like this. So the black curve is simply the impedance spectrum over the frequency range of a few hertz to megahertz. I can project this into the complex plane. So I can look at the real part of the impedance, which is simply the resistance, or the imaginary part, which is simply the reactance. And what I can do is based on relaxation processes, so chemical reactions, ion transport, I can extract the time scale from this frequency spectrum. So what we did is we applied this technique recently to a more emerging type of photovoltaic technology, perovskites. So we've done it for organic photovoltaics. I'll show you the results in a second, but for perovskites, this ended up being a far more complicated question because perovskites, in some ways, they're very similar to organic photovoltaics from the advantages. They're solution-processed solar cells, but it's a non-organic active layer. It's a perovskite active layer, a metal halide, where you can see the crystal structure here, where you have an ABX lattice structure, where we have a cation, generally lead, for the B, and then a halide. Very, very efficient solar cells made from solution. They've already gone well over 20% with the efficiencies. The problem is that they tend to be mixed conductors. So we see a mix of electrical conduction and ion conduction. And it's very, very difficult to understand actually what the microscopic processes are in these cells just based on the current voltage characteristic alone. So what we see is a dynamic, a non-stable current voltage characteristic. So we asked ourselves, can we apply impedance spectroscopy in order to, on one hand, understand these processes, and on the other hand, develop a bit of a universal model to describe photovoltaic performance from these systems. And so this was done together with Dino Klotz, who was in Japan before. Now he's at Zurich Instruments. And our goal was really to look at the entire class of perovskite photovoltaics and develop a very, very simple impedance model to describe performance. Well, it's actually not as hard as it sounds. So if we look at the full spectrum, so what you can see here is the full time spectrum, also given to you in frequency, of all of the processes that can occur in a perovskite solar cell. And what we see is very, very fast processes in green. So these are processes that we typically access with optical spectroscopy: charge generation, radiative recombination, charging, detrapping, trapping and detrapping. These are all electronic processes. And then we see processes that are much slower that we would tend to access with an electrical technique like impedance spectroscopy. For example, ion migration, chemical reactions, trap-induced recombination. And what we found is if we look in the literature at all of the spectroscopy results, in fact, most of the interesting processes, let's say most of the loss processes, are all within the range that you can measure in impedance spectroscopy. And all of the ideal processes you can access with optical spectroscopy. So what this means is we can actually use the impedance spectra as sort of a diagnostic tool to say what's going wrong in the solar cell, let's say. What we also found interesting is the electronic processes in the device are separated by several orders of magnitude in the frequency regime from the electrochemical processes. And what this means is we can actually use a very, very simple circuit model then to model these things. We can essentially use a linear circuit model to describe electrical processes on one hand at very, very fast timescales or high frequencies, and another completely separate, linearly, a completely separate circuit model for the electrochemical processes. So this is what we proposed as sort of a universal circuit model. So again, perovskites is an entire class of technologies. It's not a single type of solar cell, but we found it has a universal response because of the timescales of the processes that occur. So that allowed us to make this very simple circuit model generalized and simply be able to differentiate between electrical processes and electrochemical. And the significance of that is the electrochemical are the loss processes. So we can really just analyze this circuit model in the lower frequency regime to extract loss processes. And this is something that you can do over time. You can do as a function of irradiation, as a function of temperature. Also to look at how these loss processes evolve over time if you want to understand lifetime. Okay, so this is something that we've applied to a number of different systems, ranging from organic photovoltaics to perovskite solar cells. So Tulis is a PhD student who's just finishing his PhD now in Amsterdam, where most of his PhD was focused on trying to develop these sorts of universal circuit models for a class of different types of solar cells. But where do we go from here? So that was actually sort of the question I asked myself at some point. I got a little bit bored of electrical measurements, I have to say. And I thought there's more to it than that. Electrical measurements don't tell you the full story. Actually, what we need, especially in emerging electronics, photovoltaics is one thing, but there's many different types of electronic applications, smart materials, switchable materials, functional materials. And how do we actually characterize these type of materials? And so the idea is actually to create a new type of in situ spectroscopy, motivated or inspired by impedance spectroscopy, but connected to optical spectroscopy in order to gain more information from the system. So the idea is to couple impedance spectroscopy with an optical spectroscopy, Raman spectroscopy, which is a vibrational spectroscopy. And so you perturb your sample electrically, and then you look at the optical response. Now, the benefit of doing this is in an electrical measurement, you're just severely limited to the frequency range that you can examine. So above megahertz is essentially very, very difficult to get to because of artifacts and measurements. But if you have an optical output instead of an electrical output, you're no longer limited by these electrical limitations. So you can actually go well beyond. You have a much, much broader time scale that you can access. What it also allows you to do is it allows you to correlate electrical properties with structural properties. So why is that relevant? Well, first, let me tell you what Raman spectroscopy does. This was the simplest diagram I could think of to describe Raman spectroscopy. It's a very, very complex physical effect, but Raman spectroscopy has a universal use, essentially, in identifying structure. So what happens? So I excite my sample. In this case, it's a molecule, so this is the typical structure of a molecule. I have two balls on a spring. I excite it with light. And what I do is I change the polarizability of a molecular bond. And through this interaction of the molecular bond and the photon, I get a Raman shift. That means I have photons coming out that have a different energy than my excitation energy. It's not an absorption. It's a Raman scattering. And based on this Raman scattering, I can actually identify different chemical fingerprints or different molecular structure. So this is often used, for example, to identify drugs or chemicals or something like that. It's a very rapid screening method, very, very accurate. Now the question is, what happens if we couple it with an electrical measurement? Well, suddenly we can look at how structure changes when we apply an electrical voltage. So it means we can start to look at structural changes related to voltage. So it means we can start to look at structural changes related to electrical properties, phase changes, also heating. So the first example of this is unfortunately relatively boring to some degree. So I actually had been thinking about this technique for quite a while. How do we do it? What do we show it on? How do we demonstrate this technique? And so Sudeshna and Sheila, they were working. Sheila was a postdoc in my group. Now she's an assistant professor. And Sudeshna's just finishing her PhD. We worked with my colleague Freek, who's really an expert in Raman spectroscopy. And I said, okay, let's see if we can identify polaronic signatures in polymers. So what this means is if we have a charge in a polymer, do we see a structural change in the polymer backbone? And so what we saw is if we electrically contact polymer diodes and we excite them with light, and we measure this current voltage characteristic, so you can see it in the middle, this JV curve, what we see is that we actually get a shift in the Raman peak that follows this JV curve. So it seemed really, oh, we're really seeing the effective charge on this material. And then a colleague asked me, well, are you sure you're not seeing a heating effect, which is the worst thing that you can tell somebody when they think they're seeing a new effect. And unfortunately, he was right, but it's not as bad as it sounds. What we realized is we can actually measure Joule heating by simply measuring the Raman shift of an operating diode. So what this means, why is this relevant? Well, if we're working with soft materials or materials that are thermally sensitive, not very conductive, then we may actually want to understand how temperature affects their electrical performance. So indeed, what we see is very, very high Joule heating effects in organic electronics, up to 80 degrees, 80 Kelvin above room temperature if we simply operate a diode. This can have significant effects on the conductivity, but also the structure of the material. In the meantime, Chidi Frick, he's also a PhD student in my group. He's been extending this approach. And what we looked at now are also looking at electrochemical systems. So can we look at catalysts, the surface of catalysts? It's thought that they reorganize in situ. How can we characterize that? So what he's looking at, for example, this was together with partners at the TU Berlin, is trying to show in situ confirmation of the reorganization of catalytic surfaces while they're actually chemically active. Okay, so the future is bright. Maybe we didn't harness all that solar energy that we wanted, but I hope I was able to give you a little bit of an insight into sort of some of the challenges. I mean, first from a bird's eye view that actually without the support of policymakers, a lot of these promising technologies really don't have a chance, and even existing technologies like silicon. If we really want to actually go towards green energies, of course the policymakers have to support this. Also the question of how do we bring promising technologies onto the market? Well, we also need to work together as communities in order to define standards protocols, testing. We have to look at things that seem a little bit boring, like lifetime, and define these in order to understand where these technologies can be applied. And then in the laboratory, we really need to develop new tools, or I think we do, new tools to understand in situ phenomena so that we can use new ways of diagnosing loss mechanisms, for example, in solar cells, or even seeing new phenomena. Yeah, so with that, I just want to thank everybody who was involved. First of all, Gerald, Professor Gerlach, thank you for being such a welcoming colleague. So now we're together, two groups in the Institute of Solid-State Electronics, and also to your students who are also here today. To Agna, who joined the group very recently, thank you for having the courage to come to Dresden and start a new group. Alexander, who's not here today. Also the students and colleagues, some of them still in Amsterdam, who I was working with until very recently, Tulis, Sudeshna, Chidi, Wengrong, who are PhD students, and to Rod and Dino, who are collaboration partners, and of course to the funding. And thanks to you for your attention, and of course I'm very happy to take any questions that you have.
You cannot hear me. Okay. I'm sorry. Again, thank you very much for your very great and inspiring presentation. And now we are at a discussion. So are there any questions for Professor Van Hoof, please? Gerhard?
So from a competitive analysis point of view, how do you see this going in terms of opportunities? Yes, because I mean, there are different materials out of which you can make solar cells. And obviously, I mean, you also showed the nice development of going from 4% to 20%, but at the same time, silicon-based went to 48%. So in this positioning, what I don't quite see, is it just an opportunity for making foil-based organic cells, or is organic really going to be an opportunity that will possibly replace silicon even?
Yes, thank you very much. It's an interesting question. First of all, I don't think any photovoltaic technology will ever replace another one. What we see is there's just more and more and more. So maybe even though, for example, thin film photovoltaics, they increase their market dominance, they don't increase it compared to silicon. So the market just seems to be getting larger. So it means you don't really have repression of one technology through another. I think personally, after all the time I've spent in photovoltaics, it's a question of where the application will be used, right? Will it be space applications where price is no barrier, and then you can use expensive concentrator photovoltaics? Rooftop silicon, tried and true. Desert applications, also probably concentrator. The question for emerging photovoltaics like organics will really be reliability. I don't think it's an efficiency question anymore. I think it's really a reliability question, and being able to show, okay, we have this efficiency, whatever it is, for this amount of time, and that we can guarantee. And that's something we simply can't do yet. Yeah, so I think that'll be the big question. And that's where the groups are sort of starting to focus. How can we define reliability and improve reliability? But again, that application field is a big question. Where is the killer application for some of these newer technologies, right?
Thank you very much. Are there more questions?
Thanks a lot for this very clear talk. There was one aspect which was the efficiency, which you just said is not that big problem, but still you had this different efficiency values. So can you a bit elaborate on what are the parameters of which the efficiencies depend on? I could imagine the best use case is for the highest efficiencies. So what are the use cases which give the highest efficiencies?
Yeah, so thank you for the question. And indeed, so very, very high efficiency photovoltaics are very good for applications like space applications where weight is really critical. For almost every other application, having the highest efficiency is not actually the point. That was sort of what we wanted to do, is to see what, not how high does the efficiency, what are we shooting for, but how high does it actually have to be for particular applications? And it's not such an easy question to answer because we only have, we have standard ways of testing solar cells. It's always under something called AM 1.5, so this is the sun coming at a very specific angle at high noon, and then we have an efficiency. But what happens if I use the solar cell indoors? Right? How do I define efficiency suddenly under these type of lightings? And what we see is some type of solar cells like organics and dye-sensitized solar cells, they suddenly are very efficient under these type of lightings because they have a narrow absorption band. I think we need to know how much power does a solar cell actually have to deliver for a particular application instead of just focusing on the efficiency under standard conditions. How much power does it actually need? And why do I need the solar cell instead of a battery or instead of, some other charging source? And that was also something we struggled with, was looking for that killer application where the solar cell really was the cheap solar cell really was the best choice. Probably for wearables, but we're simply not far enough yet with wearables. It's an entire emerging market that it's not just an issue with photovoltaics, it's an issue with the entire, well, not issue, we're simply not there with wearables, but probably there is an application potential there. I'm not sure if I exactly answered your question, but I guess I would move away from efficiency for emerging technologies and look more at the needed power for that particular application under the conditions that it's being used in.
No. So first of all, thank you for this very nice overview. I have a question to the last part of your talk, the outlook, so maybe a bit technical, so where you investigate this role of, let's say, the Polaronic effect in this highly efficient perovskites and so on. So did I understand you correct that the main effects that you see are really these pure Joule heating effects? And is this one of the key elements of the Polaronic effects in this thing? And maybe a second part of this, can you see effects beyond the Joule heating with your technique, especially with this impedance-coupled Raman technique? For example, if you would cool down the anti-Stokes branch and look for excitations there or something like this, is there a chance then to learn something that goes beyond pure heating?
Oh yeah, and definitely I would be very happy. I mean, for the work that we did on the catalysts, I was very happy to see that we could see the surface reorganization. That is probably the nicest. But it was really, we did a service measurement for our Berlin colleagues. So, but I was happy it worked then. We looked for polarons for so long, and I never found them. So maybe they are still out there. I'm hopeful that they are still somewhere. I think, indeed, maybe you would have to cool the system, choose the right semiconductor, and in principle, it's the right technique to do it. I'm just starting to doubt that in some systems you can see them. So I think it's a problem of the system maybe that we used. But we could not find them despite our best efforts. Yeah. But I'm quite convinced, I thought about it a bit more. I think in something like anthracene, maybe we need to go towards a small molecule or a different semiconductor. I'm fairly sure if we have a chance, then we could in a different system. Probably polymer, the carriers tend to be quite delocalized. That might have been the problem, that it doesn't give you enough of a Raman shift. I'm hopeful. If you have a suggestion, I'm all ears. It's more exciting than heating, that's for sure.
Thank you very much for the very clear presentation. I remember you mentioned a linear model, and I remember that we also have many devices in organic materials that are highly nonlinear, for example, organic memristors. Is this, let's say, a working model for a certain small range of applicability, or can you comment this?
You mean for the impedance measurements, probably, right? Yeah, so essentially all of the systems we're looking at are non-linear, and what we try to do is then stay in a linear range that we just simply produce. So also the diode is non-linear. So just to really stay in a very, very small range where we look at the linear response. But actually another extension that's very interesting is to go to nonlinear impedance spectroscopy. But this is it's a very interesting direction to go into, but it needs completely different models. So I think that would require a small group to set up, but it's certainly something I have been thinking a lot about. Yeah. Yeah, there's certainly a lot of information going to higher orders, I think.
I'm impressed by your fitness level. That's amazing. Anyway, thank you very much, Elizabeth, for this wonderful overview. And I want to come back to the beginning of your talk when you impressed us with the sun as a resource for energy. Now, you also at one point were talking about futuristic applications, like wearable applications. You were saying we maybe don't know yet which other applications. Some of these more futuristic applications have one thing in common. It seems to me that they are extremely decentralized and out of touch with any electricity grid. And so if we are thinking about the future of energy supply in Germany and in other countries, probably at least one scenario that I see is much more decentralized energy systems than we are currently used to, with a few or a number of big suppliers, and that's basically it. But rather moving towards a very decentralized system. And so my question is, but maybe that's beyond the scope of what you would like to talk about, is is there a vision for how these very decentralized, minuscule even, sources of energy, it's more like a crowdsourcing of energy. Is that realistic, or is it completely impossible?
It's a very interesting question. So I think it is very realistic because we move more and more towards consumer electronics. And so if you don't have to hook up your consumer electronic to the grid, but you could charge it autonomously, I mean, there would be an entire market for that, likely, right? The question is, of course, on what scale we do it. I mean, a lot of people, in a way, their house is becoming more autonomous if they install photovoltaics. I think it was the vision for a long time is to decentralize energy, because energy is sort of a power concept in a way. And so if you can decentralize it, you can make people less dependent on centralized sources. With photovoltaics, of course, you're in a good situation to do that because you can really install autonomous systems quite well.
But the question is, would it be possible to get the energy converted by the variables, feed it back into whatever the grid is? So the decentralized usage seems very obvious.
Yeah. To feed it back into the grid. Oh, yeah, certainly in principle that would be... The integration part is probably the question. It's really a technical question how to integrate it into the grid at a cost that's acceptable, which sort of ties into the first point of these integration costs. A little bit of a different scenario, but essentially the same question. How do you feed it back into the grid at a low cost? But if you had a lot of people just generating energy, and I mean, it's certainly an interesting idea. Especially with the wearables. Yeah.
Further questions? There's one.
Maybe just a quick question for your calculation. Is that full life cycle calculation? So for the removal of the photovoltaic afterwards, or the removal of the power station, was that included in the cost?
Oh, sorry, I don't think I quite heard the question.
Okay, so your calculation for your energy cost or cost of photovoltaic, did it include the removal of the photovoltaic afterwards, the recycling process? Did that also include for the power stations, the recycling? We think of nuclear power stations quite expensive to recycle in the end, but was that fully included, or was it just the production and costs?
Yeah, that's actually an interesting question because it's not with silicon. You're not obliged to recycle, but of course you're obliged to recollect in Europe, but not in China, as far as I know. So I think it's a cost we neglected, but it's an interesting point because if you do the calculation in Europe, you certainly have to put whether they're recycled but recollected because it's viewed as electronics now. With the power stations. They're highly subsidized in general, so I think these low costs that you're seeing, they're also very, very artificial. I guess that the state is basically carrying all the costs of the power station with everything from start of life to end of life, and just the generation costs are what you're paying. Yeah, for photovoltaics, essentially the calculation is not that trivial when you're competing with a highly subsidized fossil fuel source. And I don't think that we considered recycling here, but I do think it's a relevant cost factor that should be considered particularly in Europe, if that answers your question.
Thank you very much. Is there further questions? So perhaps while you are thinking about questions, I might pose one. You have shown this very interesting issue that the organic devices degrade in the beginning, so drastically, around 20 to 25%. And then it goes continuously, like we would expect actually normal degradation. But what is actually behind that? So it could be now that the basic material is vulnerable to some whatever degradation, so instability. It could also be that some species are in the stack, in the layer stack, which are then after the device is packaged, start to degrade, and then there's no other species coming through because it's packaged, and maybe isolated. Do you have a clue what it could be?
Yeah. So for organic photovoltaics, what we think is in the beginning, it's actually an intrinsic process. So it's a thermodynamic instability of the active layer that's processed from solution. So you have a demixing in some cases, or a change in the morphology. And the progression after that is external stress, generally. That's the understanding. So this internal burn-in you can actually only overcome with new material concepts, which is sort of the direction the field is going into now to really stabilize the active layer with these ternary blends. So now they have 3 components, and this stabilizes then the morphology.
Okay, thank you very much.
Yeah, we still see it.
Now you had some time. Are there further questions? If not, it's actually not over. You can still have opportunity to pose questions, but maybe we change location and we go for the reception. What would you think about that? Okay, I don't see any problem with that. So then I'm very happy to thank you again.
Thank you.
Would like to take a picture.
Oh, yes.
Please, come.
Thank you very much.
Thank you.
Thank you so much.
Yeah, thank you for asking me. I hope it was somehow clear.